In this video, I will show you various examples of memory corruption bugs that can have familiar results such as segmentation fault, core dump, and memory leak. I will show you these and many other memory corruption bugs which are very scary to debug. And I will show you how to use a very simple tool called Address Sanitizer to detect all of these bugs and many more. If you want to code along with me, you are welcome to download and clone this repo. The address is in the description for starting your C++ programs and allows you to build them using Google Bazel, and it provides some example usages of very useful packages such as Google Test, Google Mock, Google Benchmark, and in this case, Address Sanitizer. So let's get started. If you have done C++ programming for a while, you probably know that it's so easy to write a code that has memory misuse. For example, in this innocent looking code that I wrote here, I take two vectors as inputs and I try to pairwise add them and create an output vector. However, if you run this code, chances are it crashes and have something that we call an undefined behavior. See if you can spot the problem for yourself. Here is another example where I create a pointer, I allocate some dynamic memory, I use it, and then I deallocate that memory. A few lines or maybe thousands of lines later, I forgot that I deleted this and I try to use that memory location again. This is a classic example that can crash your program and create an undefined behavior. Here is one more example where it probably doesn't crash your program, but it has something that we call memory leak, where you allocate a memory, you use that memory, however, you forget to deallocate memory, and as your program moves on, it will waste memory. So how can we detect bugs like this? Address Sanitizer is a tool that allows you to detect such bugs. A quick introduction of Address Sanitizer. This is a tool that's available now in major compilers like Clang, GCC, G++, Xcode, and Microsoft Visual C. Using this tool can hurt your runtime and can increase your memory usage. However, you can only enable it for debugging and disable it once the bugs are gone in production. It is widely used by a lot of C++ developers and products such as Chromium, Firefox, Linux kernel, and many others. It was originally developed by some engineers at Google, and in fact, you can find its documentation on Google's GitHub. The address is here and also copied on the description. And unlike its name, this tool should probably be called Invalid Address Reporter or Detector than Address Sanitizer, meaning that this tool can only report the bugs to you, but it cannot fix it, which is still great and is still very powerful. So what kind of bugs can Address Sanitizer detect? Here are some of the bugs that it can detect. For example, if you try to use an address after deallocating that memory location, or if you try to reference a memory location that is outside of the heap buffer that you allocated, or it's outside of the stack buffer of your program, or it's outside the global buffer of your program. And beside these bugs, it can also detect memory leaks. So hopefully by learning how to use it, debugging these bugs wouldn't be as scary and you would be prepared to handle them. Up next, how does it work? How does Address Sanitizer work? Address Sanitizer is built based on a very simple idea. Suppose I write this code when I have a pointer and allocate some memory. And later on, by mistake, I try to dereference a location that does not fall into the addresses that I allocated. Obviously, this is a bug and it can create what we call an undefined behavior. If you look at the memory map of my program, PTR will point to a location like this, which is allocated. However, PTR plus 1 is pointing to this location that is still not allocated and does not belong to my program. And as you know, this address should not be dereferenced. What Address Sanitizer does is it takes this memory and it creates a map out of it in which it highlights what location is valid and what location is not valid. So as you can see, these locations are invalid, they're marked with red, and Address Sanitizer calls them poisoned, and only these green locations are the locations that my program correctly allocated. So if this is the program memory, this map created by Address Sanitizer is called the shadow memory. If you try to dereference an invalid location in the program memory, it is as if you're trying to dereference a poisoned location in this red area in the shadow memory. And Address Sanitizer monitors this shadow memory, and as soon as you try to dereference a poisoned location, it reports that as a bug. This is done by a technique called compiler instrumentation. So what happens is that the compiler converts every write or read on my pointers to a code like this. It basically adds a check before my attempt for write or read of the pointer. It first converts my pointer to the shadow pointer so that it can look at the shadow map, and then it checks my shadow pointer to see if it falls inside a poison area or not. If it does, it reports the error. Otherwise, it moves on as usual and it performs the write or read inside the actual memory. So this code is being inserted inside your actual code by the compiler once you enable Address Sanitizer. Up next, how can we use Address Sanitizer? How can you enable Address Sanitizer in your compiler? The main flag that you should enable for your compiler is this one, fsanitize is equal to address. You can read about the details in the documentation of your compiler, either G++ or Clang, or just go to Google's GitHub documentation and read about how to use Address Sanitizer. However, up next, I will show you how to enable this using G++ and also Bazel. If you're using G++, you can use these flags. The first one indicates to use level 0 optimization so that your code doesn't get optimized out, so that if it has bugs in the part that it got optimized out, we can detect it. This one enables debugging, and this one tells the compiler to keep the information about the stack. And this one, -fsanitize is equal to address, is the most important one that enables the Address Sanitizer. You can enable these flags, and then you can give G++ the name of your file to be compiled with Address Sanitizer. If you want to use Bazel, things are not that different. You just have to provide these flags to Bazel. Rather than providing these flags in the command line, you can put them inside a file called blaze.rc and label them. Here, I labeled them with asan, standing for Address Sanitizer. And in the command line for Bazel, use this flag --config is equal to asan, which matches this label inside this file. You can see an example of this file inside the repo that I provided. Again, the address is in the description. Let's see some actual examples of the bugs that can happen and how we can detect them using Address Sanitizer. Inside the repo that I provided, there's a file called main_address_sanitize.cc, which is under the source folder and then under main. If you open this file, you will see some instructions on how to compile and build it using Bazel and how to do so using G++. And if you scroll down, you will see the main function, which reads the variable choice as a command line parameter, and based on its value, performs some actions. Each of these actions is an example of a memory bug. So let's go over them one by one and see how they work and how we can detect them. So let's compile this first using G++. You can just copy and paste this in your terminal and compile the program. Once you compile, you can just type out, the name of the executable, and then provide the choice number as a command line argument. In this case, I'm going with choice 0 first, and let's see what happens. Notice that here we have a pointer, its value is null pointer, and then we try to dereference this invalid address, which should create an undefined behavior. Once you run this, you can see that Address Sanitizer gets activated, and it shows that it detected an error. The name of the error is called segv on an unknown address. The address is 0, which is equivalent to null pointer. And it also reports in what line this error happened. In this case, it was line 61, which is exactly matching the line that I dereferenced this invalid address. So you can see that by enabling Address Sanitizer, not only was I able to detect this bug, but also I was able to find where exactly it happened. Up next, let me also show you how to run these examples using Bazel. If you want to use Bazel, just run Bazel as usual, but use --config is equal to asan. In the root folder of the repo that I provided, there's this file called .bazel.rc, in which it provides the flag that you see here to Bazel. So once you use --config is equal to asan, that means that provide all the flags that are here under asan to Bazel. And as I mentioned before, the most important one is fsanitize equal to address, which Bazel provides to the compiler, which then enables the Address Sanitizer. So I'm going to copy this command in my terminal. Note that when using Bazel, what comes after the final -- should be used as the command line argument for your executable. For example, if I want choice to be 1, I run Bazel with --1 here at the end. So that's all you need for running this example with Bazel. Once I run this, Bazel will run and it tries to build the program and run it with the command line argument 1. To run other examples on this file, just use the same command line for Bazel, but change the argument at the end to the choice that you want. For the rest of this video, however, I will use G++ and I will just use the out with the command line argument that we want. Let's run the next example. This is similar to the example before, but rather than initializing my pointer with null pointer, I just chose a random value, which I didn't get from the operating system. This value didn't come using malloc or new, so most probably it's invalid and it should create undefined behavior. Once I run this using command line argument 1, Address Sanitizer gets triggered again, and now it reports that there was segv on unknown address 1, which matches this address, and it also mentions where it happened at line 68. In the next example, I have a vector which is not initialized, its size is 0. However, I still try to dereference location 100. Let's run this example. Now I provide value 2 as a command line argument, and you will see that I will get a similar error, and the line number is now 75, which matches this line. Again, Address Sanitizer helped us to detect and find out where this bug happened. Next example is a slightly modified version of the previous one, in which I initialize my vector by saying that its size is 1. Although the size is 1, I try to access element 100. If you try to do this, Address Sanitizer again reports the error and tells you a different error, which is called heap buffer overflow on this address, which basically means that you try to dereference a location outside of the heap address that you allocated. It also gives you the line number that this error happened, line 82. And on top of this, it also provides you with the shadow memory map. What you see here is the text representation of the shadow memory, which you saw before here. This representation can be a little bit confusing, but you can easily get used to it and understand what is happening. The red zones are marked with FA, as is shown here. And each byte in the shadow memory map represents 8 bytes in the actual program memory. So what Address Sanitizer is telling us is that you have one location here that is addressable. Notice that this is not marked as a red zone, and this is the actual location that we allocated. And 01 here means this is only 1 byte. Notice that each byte here maps to 8 bytes in the actual memory. So by saying 01 means of those 8 bytes, only 1 byte is addressable. Now what we did was exceeding this address by 100. So this means we exceeded this location, went to the right all the way here, which is highlighted by the Address Sanitizer. And since each location here represents 8 bytes, so if you count the number of these bytes and multiply by 8, hopefully this will be the location that represents offset 100 from this valid location in the actual memory. So the bottom line is that we are trying to access somewhere here, which is inside the red zone. This is poisoned, and it is reported by Address Sanitizer. Let's see example number 4, which is similar, but in this case, I create a dynamic array of size 16, and I try to address element at index 16, which is really the 17th element, and it would be outside of the location that I allocated. Once you run this with input 4, Address Sanitizer gets triggered again with a similar message that says heap buffer overflow. Notice the map now has 2 addressable locations, each represent 8 bytes, which matches the 16 valid bytes that we originally had. And the location that we are trying to address, it's outside of this. It would be one after this, at this location, which is marked as a red zone and is poisoned, and that is why Address Sanitizer is reporting this. Notice that here I get a very helpful message here that this error happened at line 89, and I can go back to my program and fix it. Let's look at example number 6, in which I allocate some memory, I delete that memory, but unfortunately I attempt to dereference that deleted memory again. So once you run this, Address Sanitizer gets triggered again with a message saying heap use after free. Again, I can see the error line, and the shadow map specifies where exactly that error happened. Example number 7 is double free. I allocate memory and I delete it more than once. This can also create an undefined behavior. And once you run this example, Address Sanitizer complains and tells you this was double free on this address. It also gives you the exact line number that this error happened. In example number 8, I don't have dynamic memory. Instead, I'm misusing a static array that is allocated on the stack and only has 16 elements. However, I try to reference the element 20. Once you run this, Address Sanitizer gets triggered again. In this case, it mentions that the error is stack buffer overflow instead of heap buffer overflow, and it gives you the exact line number that this error happened. And if you look at the shadow memory map, you will see that we have these 2 addressable locations, which represents the 16 byte of the array that we allocated on the stack. And the violation is highlighted using these brackets with F2, which represent the stack red zone. The next example shows the case where you try to dereference a location that is now out of scope. I had a local variable, I store its address inside this pointer, and I try to dereference that address when that local variable goes out of scope. If you run this example, Address Sanitizer gets triggered with this error called stack use after scope. In this example, we're doing something similar by storing a local variable inside this function and then try to dereference it using this pointer. So if you look at this function, It has a local variable and it stores the address of this local variable inside this global pointer. And here we are dereferencing that location. If you want Address Sanitizer to detect this, you first need to set this environment variable to 1 using this command, and then you can run the example. Now Address Sanitizer gets triggered with the error mentioning stack use after return, which basically means we are using a location inside the stack after returning from a function. Example 11 shows the case that you previously defined a global array of size 10 and then you try to reference element with index 11. If you try this, the Address Sanitizer error message would be global buffer. Again, it will show you the exact line number and the shadow memory map. Example number 12 is very similar, except that instead of a global array, I have a static array. And again, I'm addressing an element that does not exist inside this static array. If I try to run this, I get a similar error, which is global buffer overflow. Next example is the case where you have memory leak. Here, I allocate some memory, I use it. However, unfortunately, I forget to deallocate this memory. And by the time this pointer goes out of scope, this address is lost forever and there's no way to deallocate it. Unfortunately, leak detection of Address Sanitizer does not work on Mac, which is my machine. And in fact, when I try to run this example, I get a message from Address Sanitizer that leak detection is not supported on this platform. Apparently, there are some ways to fix this. However, instead of showing this example to you guys on Mac, I will demo the example on my Ubuntu VirtualBox. What I'm showing you here is the same example on my Ubuntu VirtualBox. So let's run the example with parameter 13, which matches example number 13. Once you run this, Address Sanitizer gets triggered and it mentions that it detected memory leak. And on top of that, it mentions where that memory got allocated at line 165 in our program, which is here where we allocated the memory, but unfortunately we forgot to deallocate it. One last thing that I want to mention, if you available all the warnings for your compiler, for example for G++, I'm enabling all the warnings and also extra warnings. A lot of the memory byte issues that we detected using Address Sanitizer would also be detected by the compiler. As you can see, the warnings here are pointing to the same issues that we detected using Address Sanitizer. So it's a very good idea to always compile your code using these flags. So we saw some examples of Address Sanitizer and we mentioned that it's great. Let's talk about when and where you should use it. Obviously, you should use Address Sanitizer when you're trying to debug memory corruptions in your program. Also, it's a great idea to enable Address Sanitizer for your unit tests and also inside your contiguous integration so that as your tests run, if there is a memory issue, they are reported. Also, I would like to mention that Address Sanitizer is not a perfect tool and it has some limitations. The first one is that the memory corruption bug that you're looking for must happen in the run of your program. What I mean is that a memory bug can exist in your program but doesn't show up for a certain input. So you have to test your program and make sure you have a very good coverage of all possible scenarios so that if there is a memory corruption bug, it will be detected by Address Sanitizer. Also, one thing that Address Sanitizer cannot report is uninitialized memory read. There is, however, another tool for it, which is called Memory Sanitizer, which hopefully in some other video I can talk about it. And finally, as I mentioned, Address Sanitizer has some memory and runtime overheads, so you should probably only enable it for debugging and testing and disable it for your production. There you have it, guys. I hope you enjoyed this video. Please support my channel by subscribing, liking my videos, and sharing it with your friends. And hopefully I will see you in my next videos.